We'll start today by talking about our book. Our book is The Extraordinary Chemistry of Ordinary Things. I'll be working our way through various chapters, sometimes combining chapters together, sometimes going a little free flow, but we'll work our way through a book and hopefully learn a little bit more about science and how to talk about science in the meantime. Uh, the first chapter is called An Introduction to Chemistry. Every now and then I'll jump back and forth between just a straight up wordy lecture and maybe some slides as we go through various definitions. The book starts out with an example of electricity that we take an old style flashlight, like make a giant mag light. One that has the button on the side, we unscrew it bottom, and without that, even if the flashlight is turned on, we have no light. That's because that the electrical circuit is incomplete. We need the electrical circuit to be complete to make this flow. So, electrical circuit is the path that electrons will follow to make the light bulb light up. Now, the electrons are simply extremely small particles that will carry a negative electrical charge. They're going to run from the batteries all the way to the light bulb, and they have to complete the circuit or else they won't go. And when they complete the circuit, they generate electrical current, which is just simply the flow of electrons. And this is often measured as a rate. So you can have a high current, which would be a fast rate of electron travel, or a low current, which would be a slow rate of electron travel. The idea is that the bottom of that old style flashlight contained a little piece of metal that would touch the battery and complete the path to the side of the flashlight, so that it would carry the current, complete that circuit, and thus we'll have a flow of electrons that makes the flashlight light up. Well, the chemical experiment is, we're going to take a sponge, we're going to moisten it and try to complete the circuit using that sponge. If you're using just plain tap water, there's a good chance that that sponge won't complete the circuit. We may be told that, hey, you don't want to swim in the water during a lightning storm, but truthfully, most water, at least tap water, will only mildly conduct electricity, if it conduct at all, because there is not enough electrolytes, which we'll talk about in a second. There, we're going to try sugar water. If we put sugar water onto the flashlight, onto the sponge, and press that against the flashlight, we see nothing happens. It has not completed the circuit. But if we take some salt water, so we just take some everyday table salt, mix it into the water, and then soak the sponge in it, press it up against the flashlight, it will complete the circuit, and thus the light will turn on. We're going to, the next page talks about an extremely dangerous version of that experiment, which we'll finish up this video by doing just that. In the meantime, let's talk about what is an electrolyte, because that is the thing that is actually going to create the circuit. An electrolyte is simply a substance that conducts electricity when dissolved in water or melted. Now, a simple example of electrolyte would be sodium chloride. So when we dissolve that in water, it breaks apart into atoms, and the electricity can bounce from one atom to another and to another to complete that circuit, because the electrons have to be able to flow in order for the circuit to be completed. So these ions serve as a method of electron transport. Now, the sugar would be considered a non-electrolyte, meaning when it's dissolved, while it does break down, it doesn't break down in a way that will conduct electricity. So there's a difference here. Now, all of these things are made up of atoms and ions and molecules and chemical bonds, and we're going to discuss this as we go through semester. These, because what we really want to look at is how these two substances differ: the sugar and the salt, and they're made up of different types of atoms, different types of bonds, and as we go through the semester, we'll learn why these guys are different. Why these guys are different. The first thing we need to understand is matter. Now, matter is any substance that makes up the material things of the universe. Now, matter could be solid, could be a liquid, could be a gas. The only thing is that it is some substance. We'll look more about matter a little bit later. But sugar, type of matter. Our salt, type of matter. The atoms that make up of these guys are going to be a type of matter. Molecules, which are a group of more than two or more atoms held together by chemical bonds, they're all matter. Our ions, even electrons themselves, are a type of matter. And we'll look more about this a little bit later. One thing we need to worry about is chemistry. Now, chemistry turns out to be the branch of science that studies the composition and properties of matter and the changes that matter in turn undergoes. So we're worried about not just the things that are made up of the universe, but how they are going to change, how elements will change, how we combine things together and break them apart, and how the properties will change when we do that. Just looking at our solid, liquid, and gas situation. We take a solid, we have essentially atoms packed together in such a tight fitting thing. And as we heat it up, the atoms will split apart and be able to slip and slide over each other into what is called a liquid. Eventually, when we heat them up enough, they will actually start bouncing into the air, start bouncing around in there into a large empty space and largely not interact with each other anymore, and that they become a gas. One thing that's most important to note about chemistry is that chemistry is an experimental science. Everything we know because we've done some experiment to test this out, to understand this. We all know that ice should freeze at 0 degrees Celsius, and water should boil at 100 degrees Celsius. But the only reason we know that because we've experimentally determined that. We've heated up water, measured the temperature at which it boils, and we've seen, oh, that is 100 degrees. We've frozen water, we've measured the temperature of water, and go, oh, that is 0 degrees. What we'll learn is when we mix things together, oh, maybe that melting point changes. Maybe that boiling point changes when we dissolve things into it, water. And we know these things because we've tested them. That is part of the nature of chemistry that we have. In order to learn anything, we must experimentally determine it. There are a few key themes that will be discussed in the book. One of the first key things has to do with energy. Now, energy is simply the ability to do work. So whether we're burning fats and hydrocarbons, or we're eating food, or we're running a car, we're somehow producing or absorbing energy and doing work. Simplest type of work right here is a steam engine. Right here we have hot air coming in here, making this piston expand, turning the wheel, and then as it contracts, it's pushing the air back out as exhaust. But this giant wheel is thus connected to other wheels that can be turning things and making the power that, whether we're moving a train or we're lighting up a light bulb, all this has to do with our energy. Another theme has to do with the chemicals that make up our everyday life. Whether we realize it or not, chemistry is all around us. Plastic you have in just about anything, whether it's in your phone casing or your milk jug or even the lining of a can. You're buying a can of green beans. You think it's just a can plus the vegetable. No, there's actually a thin lining into that helps prevent it from degrading. You ever watch one of those YouTube videos of a guy dissolving a can of Coke in acid or base, and you see it becomes a floppy mess that contains the soda? That's because there's a thin layer of plastic in there that keeps the soda from interacting with the soda can. And so that's the only thing that ends up remaining once you start to dissolve the can in the acid or the base. So chemistry ends up being all around us, as we will see. Third theme will have to do with the importance of the individual particles themselves. Regardless of what particle they all have a very important role. You look at water. Water is made up of two of the simplest molecules, hydrogen and oxygen, two hydrogens and one oxygen. Yet without water, nothing on Earth could live. Plants need water, people need water, amoeba need water, everything needs water to live. You take that molecule oxygen, you put a second one on there, and you have oxygen that we breathe. We need that to live. You put a third oxygen on there, and suddenly you have something that's both dangerous for humans to breathe, but essential for human life. You have ozone. You mix ozone, put that in the atmosphere. What does that ozone do? It reacts with ultraviolet radiation and absorbs it, causing a reaction where it breaks down, and but in the process, keeping that ozone from passing through and eventually striking our bodies and causing various illnesses like skin cancer. That ozone, highly reactive, will absorb that ultraviolet light and break bonds and fragment bonds, but it all depends on where it is. Ozone in the upper atmosphere is good. Ozone on on the lower atmosphere and the troposphere, not very good. And our final theme is that chemicals can be good or bad depending on how we use them. A little bit of this could be life-saving. A little bit too much could be fatal. It all depends on how much. There's certain things that could be good because they last forever, and bad because, well, it lasts forever. As we'll see, things that we may think is good in the short run, in the long run, maybe not so good. And that, for example, plastic's harder to break down, so they can last longer on the shelf, but harder to break down when we're done with them. So we got an issue of how do we recycle them, how do we reuse them, and all that. So that is an issue that we must deal with as we move forward. Looking back at our first example and the upcoming demo that I'll attempt to do, the idea here is that why didn't the pure water conduct electricity? And why didn't the sugar water conduct electricity? Yes, we said pure water didn't contain any electrolytes. neither is sugar water. It was a non-electrolyte. But what exactly makes something electrolytic? The ability to conduct electricity is brought about by the formation of ions. Ions are simply an atom or group of atoms that will carry carries electrical charge inherent in the atom. Now, we could have a cation, which is a positively charged ion, or an anion, a negatively charged ion. Now, these charges are what will allow the electrons to bounce back and forth, that get across the solution. Now, while we have dissolved this electrolyte in water to create this effect, we could have alternatively melted it. If we had made molten sodium, sure, it would have taken several hundreds of degrees to get molten sodium, but once it is molten, if you put the current through, you would see a conduction of electricity because the atoms would be allowed to, we would have broken down to our cation and anion pairs. One thing about ions is they always will come in pairs. You cannot have one without the other. Now, things that contain ions are held together by ionic bonds, a chemical bond that results from the mutual attraction of oppositely charged ions. One of the key features of chemistry involves elements. An element we'll define a little bit better later, but just know that element is composed of atoms in a very specific way, in that each element is in turn unique. But the elements cannot easily be interconverted. Right now, if you follow the book, the book is actually a little bit wrong because we've created quite a few more elements than we see right now. We actually have not 109, but we have at least 118 elements now found. Some of these are very rare and they don't appear for a very long period of time, but there are 118 elements. Now, one of the big things about elements is they cannot be easily converted from one to another, no matter how hard we try. I mean, no, I just misspoke. They can be, but it's a process that requires extraordinary amounts of energy and unusual techniques. It is not something we could easily do. You would need to approach temperatures like the surface of the sun. You would need some sort of weird atomic bombardment. You'll need atoms moving at the speed of light in order to convert one to the other. So that philosopher's stone that was going to make lead into gold, unless that philosopher's stone was an atom smasher or some portable sun, that achievement is a little outside of our realm of possibilities. Now, what is much more easy to do is to turn elements into various types of compounds. A compound is simply a pure substance that's formed by a chemical combination of two or more different elements in a very specific ratio. Water is a type of compound, H2O. Hydrogen peroxide, which is a disinfectant, is a different type of compound made of the same two elements but in a different ratio, H2O2. You need two hydrogens, two oxygens. Oxygen that we breathe is O2. Ozone, that's our O3. So different compounds, different ratios. We have some, now you could have just a sugar, a spice, everything nice, and chemical X make something, mix on together and will form something very specific. You mix these guys together, form only one type of thing. A certain ratio controls what we find. One thing we can note about compounds is that the mass of a given compound is always the same in regards to the ratio of atoms. So looking at salt, salt always contains 23 grams of sodium for every 35.5 grams of chlorine. That's because of we'll learn about the weights of these atoms later on. If I have water, that's going to contain 2 grams of hydrogen for every 16 grams of oxygen. But if we're looking at hydrogen peroxide, that'd be 2 grams for every 32 grams, because we would have double the amount of oxygen. So that'll get us to the final slide, looking at how science fits with everything. Science is simply a way of knowing and understanding the universe. Science comes from the Latin word "scire," which means to know. So we have to ask questions in science. We have to observe the way these questions are answered. We have to ask additional questions to further understand what we've just seen. We need to interpret the answers to our questions. And then we have to communicate our knowledge to other people. All this follows under the scientific method, the process by which science operates. So, in science, we make an observation. We see, oh, it seems like the ducks will fly south at wintertime. We make a hypothesis. Maybe they're flying south to stay warm, or to nest, or to I don't know, to visit their relatives in Florida. One thing or another. Then we perform a test. We have some way of making a test. So we propose some sort of hypothesis. This hypothesis is our keenly worded. It's a shrewd but tentative explanation for a relatively small set of observations. We made our observation. We tried to guess. It's not really a blank guess. It's some sort of usually scientific guess at why this happens. So we test it. We find out, in this case, in the case of ducks flying south, we could track them, tag them, catch and release, and see where they go, and track where they go, and then maybe find them down wherever they go to, see what they're doing. Whether it's observing, just saying, okay, they're just spending time in the south, they're not nesting, they're not having babies, they're not visiting any new ducks, they're staying with their pack. We can find out all about that and then follow them back up north. See, oh, they're having babies there, or they're having babies, so we can find out more. Now, depending on whether the hypothesis is confirmed or unconfirmed, or essentially rebuked, we can then either modify the hypothesis or create a new hypothesis. But if it's confirmed and we want to perform more tests and further refine it, be better and better, we can eventually come up with what's called a theory. Now, the theory is a more firmly grounded interpretation based on a larger set of observations this is generally accepted by the larger scientific community as a whole. Not only does it fit the observations we've originally set forth, it can actually predict what will happen in future situations. We can actually explain why this is happening, not just why this has happened, but why this will continue to happen. That might have something to do, in the case of ducks, some sort of ability to determine magnetic fields, and thus they can always go to the same spot over and over. They have some homing beacon in their head. essentially that allows them to do such things. Well, eventually these theories can still be changed. They're not set in stone, but it takes a lot of work to remove them, as if they ever get to the point of a theory, they have usually enough science backing to say they are truthful, to say they are correct. But the thing about science is there's no set endpoint. There is no stop point where you say we can't have any more knowledge. There is no dead end. There's only further progression. We and the beauty of science is it changes as more science happens. We can say for one thing that this is true as of the available information, but as more information comes out, it may not be the case. So that's the one thing about science. If you ask a scientist one thing, he's not the scientist is often not going to give you a definite answer. That's because science is not always a definite thing. There's more science to be done. And if you ever see a scientist change his mind about something, that's science and work. That's scientific method. That's saying, we have more data. I need to stop holding on to this incorrect belief and move on. Now, sometimes that's really hard to do as a person. Sometimes it takes the old generation to die before that a new scientific theory can be fully accepted, because people are just too old to change their ways. But the last thing we can talk about is technology. The Greek word techne, which means art, uh, craft, or skill. Now, so technology is the art, craft, or skill that used to apply the knowledge provided by science. Without technology, science is just a theoretical field. It's like math, just taking a math major without any engineering or any physics. Math in itself is useful, but without applied math, it is just a mental, uh, um, like a surely mental work. But when we apply math, suddenly we can have all sorts of things like pipes and bridges and spaceships and guns and all that. That essentially we need science and technology working together in order to achieve what we have in this world. If you ever watched the animes Dr. Stone, the characters get frozen in time essentially and wake back up at a point in time where all of technology and everything is kind of crumbled back to the Stone Age. And so, but one of the main characters was a brilliant scientist. Even though he was a high schooler at the time, he was a brilliant scientist. And so he knows everything he needs to know essentially about how to make and recreate the world. However, without a skilled craftsman, which is a character to the right, it's really hard to apply the science. He knows how to how to put this together, what chemicals we need, what things we need to do, but we need a skilled technician to build the parts, to put them together to make essentially a Stone Age phone. Right now, the books, they're up to actually connecting the world back to the internet age through very primitive techniques, mind you, but still connect the world through various types of fiberglass wires, essentially.
Hey folks, this is Dr. Evans recording this after the fact. I want to leave you with a last bit thought for this chapter. I posed this question to students at the beginning of last year that which is more important, having a fully developed science or technology or some thereof? It's really actually hard to have fully developed one or the other because, I mean, if you wait for science to be fully developed, you're never going to make any money. But if you do the technology, you probably leaving money on the table because I mean you're playing around and maybe you get lucky, but without some of the science to back it up, you're not. You're it's a shot in the dark. And we'll learn about some of that later on when we talk about polymers. That many of the early polymers were people playing around in the lab, and occasionally someone got lucky. Maybe they profited off it, maybe they didn't. And it wasn't until things like nylon when we had a scientist come in who understood how polymers work and designed a polymer that we finally like, oh, science to back up the technology instead of the technology getting ahead of the science. But we'll leave you with this: that some, whether it's good or bad, we just went through a pandemic not that long ago, and think about like virtual learning. Case of, well, if we want to keep open and we want to keep teaching, we're going to use this technology to go try to still keep in touch with the students. Do we know this works really well? No, we don't know. We haven't had the educational studies to know how well this works, and a lot of the times after the fact, we've now that we've collected all the data, real world data, we see virtual learning maybe not be as good as it could be. If students are struggling and don't have as good access to some of the technologies, it can really hurt their scores more so than especially less affluent families get hurt more by virtual learning than more affluent families. So, was that a good thing? Probably not. I mean, but it's one of those things you can't undo the damage that's already been done. You can only mitigate further damage and try to make what repairs you can. But I'll leave you off with a demo I did at the end of this chapter.
Turned on. We got our light bulb. It's right now not connected. So when I touch this together, I have two live wires. Touch them together. See, it's incredibly bright. Now I have my glass of water. This is just standard deionized water here. If I touch these two, I gotta put them out. So well submerged. Nothing. They're both in the water, all the way in. Nothing. Put them back together. And suddenly we have light. Now here we have a sugar cube. Stick the sugar cube in. Stir this real quick. Try to dissolve this. And move it away from the mic so it's not as loud. Is it fully dissolved? No. Is it enough of it dissolved? It should be. So let's try again. Very careful. I touch. Still nothing. Nothing. Now put in just a little tiny scoop of sugar. Not sugar, but salt. Tiny scoop of salt. I wish I had a salt shaker, but bakers can't be choosers. this up to the camera. Not very much. Not very much at all. Dissolve that in. There we go. It's lighting up. That's because, as we see, salt is electrolyte, sugar is a non-electrolyte. So we will leave you with that for now.